Since in this course we're going to be talking about different programming languages and comparing them, we want to start off by talking about some common characteristics of all programming languages, and that'll give us a framework to discuss how different languages are related. So we'll talk about how we evaluate programming languages, the structure of programs in those programming languages, especially the syntax and the semantics of the language. We'll talk about type checking, and we'll talk about orthogonality. So when we evaluate languages, there's lots of different criteria we can use. The first would be reliability. How likely is a program written in that language to actually work? How secure is it? That sort of thing. Then readability indicates how easy it is for someone who's not the programmer to read and understand that language, or how easy it is for the programmer to understand code they wrote several years prior. Writability is concerned with how easy it is to write programs, how many options you get, and then once you have those options, how you're combining those to actually make a program. Reusability is how easy is it to take code that's already exists and to incorporate that into a new program. And finally, efficiency is how fast the program works. Now, in general, this list is in decreasing order of importance. For the most part, in most situations, reliability is a lot more important than reusability or efficiency. However, that's not always the case. Each individual application has different priorities. And so we'll do a lot of hedging what we say because, again, most of these things aren't universal truths. They're things that are usually the case. However, again, every application is different. So there's cases where efficiency is the most important thing, even if it's not 100% reliable or if it's not readable and so forth. So when we talk about reliability, readability, writability, reusability, efficiency, what sort of things impact those considerations? Well, the first would be control structures. That would be things like loops, conditional statements like a switch, and so forth. Those can definitely have a big impact on how we evaluate the language. Data types, the same thing. For example, a language that has an actual money data type is going to be much better for banking applications than a language that doesn't have a built-in type that forces you to use integers or even worse floats to represent money. Different types of syntax certainly can lead itself to improved readability and writability, but also reusability and in some cases reliability because you can have syntax that enforces practices that are safer and more reliable. Also, support for abstraction can certainly improve reusability and in some cases the readability and writability as well. Type checking can definitely impact reliability and it also can affect writability when you talk about strong versus weakly typed languages, which we'll talk about later in this video. And then exception handling improves reliability because it gives you a language construct to handle unexpected situations. And of course, there's other things that can impact these, but these are some of the most important and the ones that we'll be talking about in this course. Now, every programming language has some sort of structure for its programs, and we can talk about that structure at different levels. So the bottommost level would be the lexical level where we're talking about the tokens of the language. That would be the things that are the building blocks of the language. So things like operators, separators, literals, comments, keywords, identifiers, and you can see some examples here. Now these aren't all for the same language. So for example, in some languages, they might not have a colon as a separator, and certainly comments are different in each language. And sometimes there's a misunderstanding about the difference between a keyword and an identifier, and they both represent names in the language, but the keywords are the ones that come from the language itself, whereas the identifiers are ones that the programmer comes up with. So suppose you declare a variable called tree. So that tree would be an identifier. A keyword would be something like for, which is used in a for loop, or if, that you would use in an if statement. So the keywords are the names that come from the language. Identifiers are names that the programmer comes up with. Then at the syntax level, we're talking about how the language itself is structured. How do we put the tokens of the language together to form statements that are valid in the language? And we'll talk about some ways to specify that later in this video. The contextual level, you'll sometimes see referred to as the static semantics of a language. And that's basically the things you can determine about the semantics prior to the program actually executing. So things like variable declarations, their types, how they're initialized, that sort of thing. You can determine that just from the code. So it's semantics, not syntax, but you can still evaluate it during compile time. And then finally, the semantics of the program are the meaning of the program. It's what's going to happen when you run the program. And sometimes there's a confusion between the syntax and the semantics. And the way to keep that in mind is you can have valid syntax that's poor semantics. So for example, you can have a valid statement that's adding two variables that's syntactically valid, but if one of those variables is, let's say, a string, and one of those variables is a class object, then when you add them, there might not be a way to do that in the language, and so semantically it's incorrect, even though syntactically it is correct. So there are several ways we can define the syntax of a language. So one of the ways we can define the syntax of a language is with what's called Backus-Naur form. You'll also see this called BNF. There's also an extended version called eBNF. And it was developed in the 1950s as a way to exactly express the syntax of a programming language. Specifically, in this case, it was ALGOL. Our BNF specification is a set of derivation rules where we have a symbol and then this : equal and then some expression. So there's two types of symbols there. The symbol is a non-terminal that appears on the left-hand side, and it appears in the grammar, but not in the actual program itself. Whereas the expression is a terminal. It does appear in the program. It's the tokens that make up the language. Now, if we have multiple expressions that we want to correspond to a symbol, we can separate those with a vertical bar. And the way it works is we replace each symbol on the left with one of the expressions that are on the right. So here's an example BNF where we have something that describes the syntax for some assignment. So an assignment, as you can see, is a variable followed by an assignment operator, followed by a value, followed by a semicolon. Now the value is either an assignment or it's a variable or it's a number. You can have non-terminals on both sides. And then our variables, assignment operators, and numbers are defined as you see there. Now the thing to keep in mind is you cannot have anything that appears in your language other than the tokens specified on the right-hand side. So everything in the language has to come from these values. So here's a few examples. So which of these are valid? Well, the first statement, C equals 3, we have C is a valid variable, the double equals is a valid assignment operator, and the 3 is a valid value. It's followed by a semicolon, so it's correct. Now the second example, we have Z, a valid variable, but the single equals is not a valid operator in this syntax, so that's syntactically incorrect. In the third case, 3 is a valid number, but it's not a valid variable, and according to our syntax, we have to start our assignment with a variable, so that's not valid syntax. And then finally, we have J equals A plus equals 3. J is a valid variable, the double equals is a valid assignment operator, and then A plus equals 3 is also a valid assignment, and notice that an assignment is a valid value, so this is valid syntax. So in this next set of assignments, K equals 9, K is a valid variable, double equals is a valid assignment operator, and 9 is a valid value, so that's valid. A single equal, that makes it not valid, so that's invalid syntax. So for the third one, we have N times equals R. N is a valid variable, times equal is a valid assignment operator, but R is an invalid variable, and we're also missing a semicolon, so this isn't valid. And then finally, we have C equals 42. Again, the single equal sign is not a valid assignment operator, so that's an invalid syntax. Now, another way to define syntax is with a syntax graph. So here we have the syntax graph for an if statement, where we have if, which is followed by a condition in parentheses, followed by one or more statements, followed by a semicolon. And then notice we have this optional else statement, which again would be an else followed by some statements, followed by a semicolon. Here's one for a switch statement, where we have a switch followed by an expression in parentheses, followed by a opening brace, and then notice we have a closing brace at the end. Then the switch is followed by one or more case statements. Notice the arrow says we have to have at least one, but we can have as many as we want because we can keep circling back. And then we have an optional default statement at the end. So next, let's talk about data types and type checking, which is a really important consideration in the language you choose. So data types are defined by a set of legal values for that data type, the values that that data type can hold, and then the operations that you allow on variables of that particular type. So some examples that you should be familiar with, you can have integer types, real types, array types, string types, and many others. You can also have user-defined types. Now, type checking ensures that when we have variables that we're using in an operation, that the types are valid for that operator. Now, some types are actually equivalent, and there's multiple types of equivalence. For example, structural equivalence means that the types have the same set of values and operations, or in some cases that one type is a subset of the other type, and so in those cases you can sometimes use the first in place of the second. And of course, the strictest type of type equivalence would be name equivalence, where the two types have the same name, meaning they are the same type. So if we have two types that have what seem to be equivalent values, here we have an int that's equal to 3 and a float that's equal to 3.0, which are values that are equal. But we need to think about how our program is going to see these. So Typically an integer is going to be represented by some bits in memory, and we'll have the 1 and the 2-bit set so that you get 3. So this is the binary representation of the integer 3. With floating point numbers, it's not quite as simple because they have an exponent part and they have a fractional part. And the key you need to see here, though, is that they're represented differently. Because of that, we can't treat these areas of memory the same. So if the types are not equivalent, there's a couple things we can do. We can throw an error. We can force the programmer to cast to change one form to the other. And in that case, usually you would convert the value 3.0 float to the integer value 3. And notice again, those would be different in how they're represented in memory. You can also have coercion where you have an implicit cast, and that'll do that conversion without you having to specify it. Now, which is better, again, just depends. But when you have a less strongly typed language, you can run into problems if you're doing these implicit conversions all over the place. So a strongly typed language is one where every name has a single type associated with it. And when I say name, I'm talking about a variable name. The type that that name is associated with is known at compile time so that we can generate type errors at compile time. You don't have to run your code to find out. If you've ever done Python programming, you can maybe see the benefit of that. And of course, various languages have different levels of type checking. A language like C has some type checking and it's strong in some ways, but with pointers and things like that, we can get around almost any type checking that occurs. So it would be less strongly typed than a language like, let's say, Java, but it would be more strongly typed than something like Python, where in Python you can have a variable x, and then you could say x is equal to 10, and then you could say x is equal to a list, and you could say x is equal to a string, all in the same function. Now, the benefit of strongly typed languages is that you get more reliability. It's more likely that your code will run. The downside is your code is less flexible, and so which of these trade-offs is the way to go really just sort of varies. And typically in industry, we go back and forth of what type is preferred. So for a while, less strongly typed languages were preferred, but then people started running into problems with those. So they said, hey, we need to have strongly typed languages because then we don't have these problems. Then the pendulum swings back and it goes back and forth. I think right now in industry, as I speak in the year 2022, we're swinging back more toward strongly typed languages being in favor. But again, eventually we'll probably swing back to the less strongly typed languages being in favor. And again, whichever one is best for you depends on your application and what type of trade-offs you're willing to make for your programming language. So the final topic in this video is going to be orthogonality. Now, orthogonality tends to throw people off. Don't spend too much time worrying about this. Just know that this is a concept that exists and do your best to get your head around it. But if it's something you struggle with, it's not that critical that you understand it for CSC240. It's just something that you want to be aware of in general. So two vectors are orthogonal if they're perpendicular. Notice they don't touch very closely. Well, when it comes to programming languages, orthogonality describes how we can combine elements of a programming language. So if we have an orthogonal language, they tend to have a small set of constructs, and we can combine those constructs in consistent ways. So that leads to languages with simpler syntax. To give you an example, C is a less orthogonal language. So what can we use as a return type? Well, here we have a function that returns an integer and a function that returns a struct. Don't worry if you don't understand the code, just know that that's what's going on here. This first function returns an int, the second function returns a struct, which is a user-defined type, similar to a class, and we'll get to those when we cover C. However, while C does have arrays, you can't use an array as a return type, and you'll notice here I'm trying to return an integer array of 5, and I'm getting an error. So C is not orthogonal when it comes to return values. Now with scheme, it's more orthogonal. I can return integers, and I can also return lists, which are similar to arrays. But I can also even return a function. And again, I don't expect you to understand how this code works yet. Just know that this is a function that returns a function. And so here's my output, and you'll notice when I just call that function, it returns a procedure, and then I can actually use that procedure to call that function with some parameter. So in this case, function returns a function that when I call it with double, that doubles 1 plus the parameter. So 1 plus 10 is 11. When you double that, you get 22. So that scheme is a very orthogonal language. It has a very simple syntax. In fact, when we cover scheme, we'll cover most of the syntax you need in about 3 or 4 minutes. So that's a quick introduction to some of the characteristics that are important to understand about the languages you use, and it should give us some insight into how we can compare languages in the future.